All right, let's jump right in. Welcome to this explainer, where we're going to unpack a genuinely fascinating May 2026 paper by astrophysicist Satish B. Thorway. We are looking at a concept called dynamic vacuum field theory, or DVFT. And honestly, if the math holds up here, it could completely flip our understanding of the universe's architecture totally on its head. So let's explore this together. When you look up at the night sky, it's totally natural to think the real action is wherever the light is, right? The stars, the galaxies, those massive clusters. But the vast majority of our universe is actually made up of these colossal, dark, silent spaces that we call cosmic voids. And that brings up a massive fundamental question. What if those voids aren't just empty nothingness? What if they are actually active, powerful structures that are literally pushing the universe apart? So let's kick things off with Section 1, the mystery of cosmic voids. Now, standard cosmology, specifically the lambda CBM model, treats these voids as passive statistical underdensities. Basically, the idea is that matter clustered together over billions of years, and it just left behind these big empty pockets. And to be clear, the standard model isn't entirely wrong. It does a great job explaining a lot of what we see. But DVFT proposes a much deeper physical origin. It argues that these voids are not passive leftovers at all. They are active vacuum gravity hills. So instead of just lacking matter, the vacuum of space in these regions is actually structured in a way that actively repels matter. Moving right along to Section 2, the dynamic vacuum. Okay, to really grasp how empty space can push stuff around, DVFT asks us to stop thinking of the vacuum as a void of nothingness and instead treat it as a complex amplitude phase field. Think of the vacuum as a fundamental fabric, a substrate that has two key properties, amplitude and phase. The paper represents this mathematically, showing that the amplitude governs how things respond to gravity and inertia, while the phase carries the structural, topological memory of the universe itself. In this theory, spatial gradients, meaning changes in the vacuum's amplitude, are what actually create the physical effect we feel as gravity. Satish Thorway actually summed up this crucial point perfectly. He wrote, "Phase winding gives topology. Amplitude response gives well or hill." In simple terms, the structural arrangement of the vacuum, its phase, sets up the scaffolding. But it's the amplitude, whether it's enhanced or depressed compared to the cosmic background, that physically determines if a region in space acts as a gravity well pulling matter in or a gravity hill pushing matter away. Which brings us to Section 3, wells versus gravity hills. To understand where these hills even came from, we have to rewind all the way back to the primordial universe. Initially, right after the Big Bang, the vacuum is in this super unstable state. Then it undergoes what physicists call a tachyonic roll-down, transitioning into a stable state. But because this happened so incredibly fast, and the universe is, well, huge, the phase of the vacuum couldn't synchronize everywhere at once. Imagine a lake freezing over really rapidly. The ice crystals form in different directions and crash into each other, creating stress lines and trapped bubbles, right? The early universe did the exact same thing, freezing its phase mismatches permanently into place. Physicists call this cosmic flash freezing process the Kibble-Zurek freezeout. It's the mechanism that trapped these primordial phase mismatches into a permanent network of cosmic defects. And these trapped defects form the foundational architecture of our entire universe. Some defects became amplitude depressed. Those are our gravitational wells. Others became amplitude enhanced, and those are our gravitational hills. So what does this leave us with today? It literally gives us the cosmic architecture we observe right now. The amplitude depressed Kibble-Zurek wells, they trap baryons, ordinary matter, and they eventually seed the galaxies, clusters, and filaments where we live. But the amplitude-enhanced Kibble-Zurek hills do the exact opposite. They suppress baryons, and because these hills are naturally broad and diffuse, they expand to seed those giant cosmic voids. This is a perfect explanation for why voids dominate the volume of our universe. Gravity hills are just simply wider and more volume-filling than compact gravity wells. And there's a really elegant equation for this. In DVFT, gravity, represented as g, is a response to the spatial gradient of the vacuum's amplitude. Inside a gravity hill, the vacuum amplitude is highest at the center and decreases as you move outward. This means the gradient mathematically points inward. But because of that negative sign in the equation, the resulting gravitational acceleration actually points outward. It physically pushes matter away from the center of the void and out towards the edges. Next up, Section 4, galaxies inside voids. Now, you might be wondering, this brings up a bit of an apparent paradox.
If cosmic voids are giant gravity hills acting like cosmic snowplows, pushing matter away, why on Earth do astronomers sometimes observe isolated galaxies just surviving deep inside them? Well, the solution is incredibly elegant. Void galaxies are just local Kibble-Zurek wells embedded inside larger Kibble-Zurek hills. It's a nested structure. Because gravity wells are very compact and hills are incredibly broad, a small, intense gravity well can safely trap its own local matter and hold onto its galaxy, even while it's sitting inside a massive, repulsive cosmic void. The void is globally suppressing matter, sure, but locally, the well is holding its ground.
All right, Section 5, explosions at the edge.
Astronomers have recently been tracking these wild phenomena called LFBOTs, luminous fast blue optical transients. These things are extremely rare, massively energetic, rapidly evolving cosmic explosions, and they are huge mysteries. Their massive energy outputs, their blue color, and especially the strange places they occur, often completely challenge our standard models of supernovas. Standard physics really struggles to explain where they get all of this energy, especially when they pop up far away from heavy star-forming regions. Here is where DVFT offers an absolutely breathtaking explanation. What if an LFBOT is actually the explosive result of a gravity well rubbing up against a gravity hill? The theory suggests a rare partial annihilation can happen at a well-hill boundary. When these opposing topological defects clash, even if it's just over a tiny local patch of maybe tens of parsecs, they release massive, massive amounts of vacuum gradient energy. And the crucial takeaway here is environmental. DVFT predicts these huge explosions should happen exactly near the edges of voids and filaments, where baryons are sparse, which, amazingly, is exactly where some of the most anomalous LFBOTs are being found.
Which leads us to our final part, Section 6, testing the theory.
Listen, a beautiful theory is just poetry until you can back it up with hard data, right? When we compare the observables, we see distinct, measurable differences between the standard model and DVFT. While the standard model says void volume dominance and negative lens convergence are just passive results of missing matter, DVFT interprets them as active features of Kibble-Zurek gravity hills. More importantly, DVFT predicts specific active structures, like sharper compensation walls, where the pushed matter literally piles up at the boundary of a well and a hill. And that gives us something absolutely crucial in science: falsifiable predictions. To prove DVFT, upcoming mega observatories like the Euclid and Roman space telescopes need to look for these exact phenomena. They are going to be hunting for coherent void lensing residuals. They look for central negative convergence, meaning the light is bending in a way that actually suggests a repulsive center. They'll look for those structured boundary compensation walls and embedded positive wells deep inside the voids. It really all boils down to one single decisive mathematical test. You take the observed lensing data, and you subtract the predictions made by standard dark matter and neutrino physics. If the resulting number, the residual structure, is 0, then standard cosmology is sufficient. We don't need a new theory. But if there is a coherent residual left over, that is the smoking gun. It means DVFT is real, and the vacuum of space is an active, structured hill pushing matter away. So I want to leave you with a thought here. If that residual structure is found, it means the very fabric of empty space has a complex, invisible architecture that dictates the flow of entire galaxies. And if cosmic voids are actually giant gravity hills built in the first fractions of the second of the universe, what else is hiding in the vacuum? Thank you for exploring this fascinating paper with me. Keep wondering, keep learning, and as always, keep your eyes on the data.